Hello again. It's 10 a.m. on a day that starts with a T, so it's time to look at some API review. Today we're looking probably only at new API regarding IEEE 754, the 2019 version, and hopefully we actually finish it. There's a risk that we'll have to cut things short if we don't have enough people when the hour rolls over. So, Drew, you're up.
Yeah, I'll give a sort of a brief overview to start. This is the proposal to add the IEEE decimal floating point types to .NET. So notably, these are in addition to both the binary floating point types that we already support, as well as the system.decimal type that we have supported for the past couple of decades. Currently, the proposal is to include these in system.numerics to prevent confusion with that existing decimal type, although that is up for debate. In terms of motivation, just to briefly break it down, I think there's two main arguments for why these types would be a good addition to .NET. The first argument is decimal floating point arithmetic is beneficial to users over binary floating point arithmetic. And then the second argument is conforming to the IEEE standard is beneficial to users over spinning up a sort of ad hoc type that only exists in .NET, which is basically what system.decimal is. And I can elaborate on both of those points as needed. But in terms of this API proposal, I've outlined decimal 32 because the other two are almost duplicates of decimal 32. The couple points where there are differences I called out in the API proposal. There are some alternate designs that are up for debate. There's some risks that I want to mention. I guess where should we start? What would you all like to talk about?
I mean, the thing at the top is introducing a new type of number altogether, so
Yeah,
seems like a reasonable
sure.
place to start.
We can
Also,
start
what's all
with the
this
interface.
platinum that you've written all over the place?
Yeah, so maybe I'll actually start with the alternate designs because that will add some important context there. So a few APIs in this review have been annotated with just this platinum keyword. They essentially represent high implementation cost functionality that's only recommended by IEEE. So these are APIs that we're going to want to approve today, but we don't believe that they are essential to ship the type. So there is likely a world in which we ship the type without the platinum APIs and then add them later as needed. But we want to consider the type as a whole, assuming that this is sort of the end goal.
Just to elaborate on that point
go
in
ahead.
particular, these are APIs like sine, cosine, exponential power functions, things which are core to the concept of floating point, but which the cost of implementing them is going to be high enough that we're not convinced we'll be able to get them all implemented in .NET 8. And so there'll be things that we will definitely be implementing and providing. It's just it might end up being that we ship the core of the type in .NET 8 and then add the trigonometric functions in .NET 9.
Yeah, exactly.
So that means that we should look to this with an eye toward expanding it in the future. So future-proofing, basically.
I would say so. I would say what we have proposed is the entire API service that we strive to reach eventually. And the annotated platinum APIs might not ship in .NET 8. So it's worth considering, I suppose, if we are okay with shipping this sort of 90% of the way there kind of API, or API service, I should say. So the other thing I'll note before we move into these is that the proposal covers all three types. There's definitely an argument for focusing on just one of them or two of them for .NET 8. Decimal 64 we believe to be the most useful of the three, based on the precision that it can represent, the range of values it can represent, as well as the reasonable size compared to decimal 128. I think from there, I'm leaning decimal 128 is the next target, and then 32, but that's also up for debate, and that's sort of an implementation detail more than anything. Let's see. Yeah, okay, I think that's everything that we need to touch on, and we can move into the API itself. So starting off with this interface, this represents the end goal, meaning a full integration into generic math of these new types. We have an interface currently called binary floating point IEEE 754 that has the same inheritance of floating point IEEE 754. Essentially the floating point IEEE 754 inherits from all of those advanced math functions that I referenced earlier in the platinum tier. So that's the sine stuff, the exponential stuff, the logarithmic stuff. So this interface is, we aim to ship this once we've reached that point where we can support all of that extra functionality. Before reaching that point, as you can see in the decimal 32 inheritance, it will just be inheriting from floating point, which is what system.decimal currently does. That sort of makes sense. I can elaborate if needed.
Right. So all the trig functions are on the IEEE 754. So this is saying no trig. And if for some reason you decide to do trig without whatever quantization means here, then this would jump up to IEEE 754, and then if it takes 3 waves, then it would jump up to this one.
Yeah, notably, those 3 APIs in that interface are going to be exposed regardless of whether the interface exists on the types themselves, because they're required by IEEE for the decimal type specifically. And we can discuss what exactly those do when we get to them in the actual type.
Browser crash, one moment.
No worries.
Okay. All right, so what is this?
Yeah, go ahead.
So, do quantize and quantum, would they make sense as names to people who want to use them? Because looking at them, I would have no idea what these things do.
Yeah, so that's up for debate. These names are directly taken from the IEEE spec. So for users that are expecting us to behave in similar ways to other languages offering these types, that might be what they're looking for. Just to give an overview of what they do, quantize takes in 2 decimal, actually backing up for a second, the IEEE decimal floating point types have what are called cohorts, which basically means you can represent 1.2 and 1.20 as 2 different numerical values that are numerically equal but represented differently. And that allows you to sort of encode significant figures. Notably, system.decimal is set up in a similar way, where 0, for example, I think has 28 different encodings based on how many significant trailing zeros there are. So all of these new APIs are based around that concept because they don't exist. That concept doesn't exist for binary floating point. So quantize takes in 2 decimals, and it attempts to change the quantum of the first one to match the second one. And I'll actually just read straight from the spec because I think it's clearer. For finite decimal operands x and y of the same format, quantize xy is a floating point number in the same format that has, if possible, the same numerical value as x and the same quantum as y. And the quantum is defined as it is a number. Sorry, this is a little bit tricky to explain. It's essentially it's a number that's encoding the exponent value of the decimal type. So specifically, it is a decimal type itself, but it is 1 followed by as many zeros are necessary. Actually, sorry, it's just the number 1 times 10 to the exponent.
Right. So to maybe explain this a little bit more simply, quantize is basically copy sign, but for quantums. So copy sign takes the value of x and gives it the sign of y. In the same way, quantize is effectively copy quantum in that it takes the value of x and gives it the quantum of y. And so if you had a value 1 and another value 1.00, then you can effectively say that you should translate the 1 to have the same quantum as y, and therefore make it also 100. So it basically allows you to normalize the number of trailing zeros that exist or not. It's something that people have asked for on system dot decimal for a long time because they might have 0.00000 and they want to normalize it to just 0 or to just 0.0. And so that's what it allows you to do. It allows you to normalize the number of trailing non-significant digits.
Yeah, exactly. Thanks for the much better explanation. And I can, if people would like, I can send the specific wording from the spec if that would be helpful.
Well, I mean, this is one of those things where the description of you saying what it does, ignoring that the notion of significant figures may or may not be called quantum, because I think you also said cohort. Ignoring the word quantum, the verb quantize doesn't mean to me anything of what you just said. So,
yeah,
like, I'm aware that this is the verb from the IEEE spec, but now we have is this the word to use? And I don't, maybe it is because it's from the spec and we're being the type from the spec, but it's certainly, I would look for normalize or normalized significance or, something along those lines.
It's not necessarily obvious. However, it is the specified wording, and it's the wording that other languages that are adding or have already added the support for these types are normalizing on. So it's going to be an industry standard term. We could certainly provide an additional function that had a clearer name if we thought that was worthwhile, but I think it's important to not deviate from the spec on this particular point, since that's the thing that people are going to end up learning across everything else.
Yeah, I agree with that assessment because we do it with other APIs too that are very domain specific.
Okay, quantum is not a verb, so that's not an appropriate method name.
We would probably want to call it,
right?
Yeah.
I was gonna, unless this quantum verb is doing something other than getting the quantum.
It's just extracting the quantum from it.
Would we, in the same sense, want to change same quantum to is same quantum?
Or has same quantum.
Has same quantum, yeah.
Or have.
Yeah, because it's 2 values. It's a comparison between 2 values.
Right, because it's static, not instance. It's not x has same quantum as y. It's do x and y have the same quantum. Yay, conjugation.
Let me confirm that it's bidirectional.
Just for my own understanding, the quantum is the exact same value, or just the same degree of value? Is like
It's so
sorry,
the quantum is exactly 1 times 10 to the power of the exponent stored in the value. So quantum of 100 would be the decimal value 1 times 10 to the second, for example.
But 100 and 100.0 don't have the same quantum.
Yes, because I believe 100.0. Right, double check. Tanner, do you know this one off the top of your head?
Right. So the quantum is basically trying to give the 100 and 100.0 have the same exponent, but they do not have the same quantum because the underlying significand is represented differently, and therefore the underlying exponent of the represented value differs. They'd be off by the quantums would be off by an order of 1 between the two of them.
And similarly, 100.0 and 100.1 do not have the same quantum.
Correct. I believe that is correct.
Actually,
Wait, what?
I think
no.
those two would have the same
Yeah,
quantum.
I was good.
Yes.
That's what I'm trying to understand. Is
Yes.
it purely like number of significant digits, or is it both number of significant digits and what those digits are?
I think it's purely number of significant digits.
Like, does the value of get quantum tell you basically, or directly or indirectly, the number of decimal digits that will be printed after the decimal point? Is that the number it is?
I believe effectively. I don't remember the entire math off the top of my head for exactly what it.
It will tell you the number of decimal digits represented before and after the decimal point.
So 1,000 with 1,000.0 and 100.0 have different quantums.
Yes. So 1,000.0 is going to be represented as 10,000 times 10 to the negative first. So the quantum in that case would be 1 times 10 to the negative first. 100.0 is going to be represented as 1,000 times 10 to the negative first. So the actually, no, you might be right there. I think the quantum of both of those would be 1 times 10 to the negative first. In which case, yes, your original statement was correct, that it's trailing zeros, I believe. Trailing digits.
Right, because it's sign, coefficient, and quantum, where coefficient is effectively the raw significand, and the quantum is then the actual exponent minus the number of bits represented. So if the significand of both, since the significand of 1,000 and 100.0 is both 1,000, you have the same coefficient for each, but you have a differing exponent, but then the same quantum.
Okay.
And I put the spec wording in the chat if people want to look into that more specifically. And for people watching, the 2019 IEEE spec has these in 5.3.2 and 5.7.3.
Quantum is the most confusing part of the decimal spec.
Yeah.
for at least for what it publicly exposes.
For the other values in these descriptions, you talked about a triple of quantum exponent and coefficient. We're exposing quantum here, are coefficient and exponent also exposed somewhere?
Those are exposed conceptually through floating point IEEE 754, in that you are allowed to extract the underlying raw exponent, or not raw, but the underlying unbiased exponent and the significant.
So, chat asks, should quantum, instead of a static method, should it be an instance property? I assume it's not cheap enough to want to be a property.
It's not just the aspect of how cheap it is, but there's also the aspect of instance properties on value types is potentially expensive, and comes with negative impact to codegen and general performance. And so for primitive like value types, we have often exposed these things as static methods, like float.isNan instead of x.isNan.
Fair. All right. So, does anybody have anything left aside from thinking that the notion of quantum is, well, a terrible word for them to use, and B, confusing as all get out? Does anybody have anything left on the naming?
We had already talked about turning the words into verbs rather than nouns, and that seems okay to me.
Yep. So I put quantum becomes get quantum, and same quantum becomes have same quantum.
Just one more thing on quantum. Why does it return T self rather than like int?
Because it returns an instance of the type that is the encoding of 1 times 10 to the exponent.
This is basically similar to the concept of in binary floating point, there is a function called I'm going to get this wrong. There's fmod and mod f, and they do similar but different things. One of them splits the floating point value into the integral and fractional parts, but the integral part is still returned as a floating point because it is always exactly representable. And when there is hardware support for these types, the hardware that supports it prefers not to change the domain of the register, with floating point types typically having a different register than integer types. And so it in general makes it more efficient to use and then later handle in subsequent computations by keeping it as an exactly represented decimal value.
Okay. And then my next question is, for same quantum, is that operation logically different from get quantum 1 equals get quantum 2? Or get quantum x equals get quantum y?
I do not believe so.
Do we need both? Or is it like somehow significantly more efficient to have it, or?
It's a function, so it's an individual function from the concept of IEEE, and there are particular optimizations that hardware can do. It is something that users could manually do, and if we get hardware support in the future, we could optimize behind the scenes in the JIT. But in general, for these types, when the spec has had something as strictly required for an API, we provided it from the spec standpoint.
Yeah, it's also worth noting that there are some edge cases regarding non and infinity that same quantum has to encode, but you wouldn't necessarily be able to do that just by getting the two quantums and directly comparing them.
Those are special cases that are specific to quantums and not generally apply to equality on decimal 32, 64, or 128.
I believe so. So the one edge case that I'm looking at is that's relevant here is same quantum of two nons is true.
And equality on two nans is false.
Right. And extracting the quantum of a NAND doesn't necessarily get you an actual quantum.
Okay, so same quantum is actually not just get quantum x equal get quantum y because of
Yeah.
NaN.
Yeah,
And
exactly.
infinite.
Well, it says if x is infinite, quantum of x is plus infinity with no exception. So infinite seems like it'll work out fine.
Yeah.
Plus and minus infinity apparently have the same quantum. I guess they are both 0 and infinite precise at the same time. So makes sense.
Yeah.
But the fact that the quantum of infinity is infinity, it does explain why get quantum can't just return basically the exponent. And yeah, I guess I'd also assume that in hardware they're going to implement same quantum as two floating point registers as inputs and write the result into a whatever the non-floating point registers are called. So I'm guessing this will save a floating point overwrite over calling it quantum manually. All right. Did that get all your questions answered, Steve?
Yeah.
All right.
Great. So moving through the type, again, I do think that's going to be the hardest thing we're going to discuss today, besides maybe the constructor. Decimal 32 inherits basically everything that half, etc. inherit, except for it inherits I floating point instead of I binary floating point IEEE 754, which we already discussed. Internally, 32 is represented with a uint, ulon for 64, and uint 128 for decimal 128. Moving through parsing, this set of parse functions exactly matches what half exposes. So some of these are coming from a number base, some from iParsable, iSpan parsable, and then some were just exposed because the other type also exposed them to sort of match that logic. This grouping of miscellaneous methods, they don't fall into any specific, or they fall into a couple of different interfaces. So the thing that stands out in this section is probably encode decimal and encode binary. I guess this will be the second thing that might need a little bit of discussion. So the decimal types for IEEE, the spec comes with two different forms of encoding. There's the binary encoding and the decimal encoding. And notably, they're still both encoding a decimal number, but the binary encoding is basically it codes the mantissa as an integer, as a binary integer, whereas the decimal encoding has a more complicated, densely packed decimal form of encoding the digits themselves. So I think
is one of
yeah, go ahead.
Sorry, is one of those two just returning underscore value?
Yes. Let's see, I think decode, encode binary is just going to return underscore value.
Okay.
Decode binary is going to sort of do the opposite, and that could be argued to be a constructor if the user is sort of spinning up their own encoding, but that's not a very usable constructor. I think that these exist mostly for like interop reasons, right? If you want to get the underline, if you're working with IEEE decimals that are encoded in the other way, then you would use this functionality to convert it to what we support, which is the binary version. So if you're reading from some database that has IEEE decimals encoded as a densely packed decimal, you would use decode decimal, inputting that raw value, and then this API would output a decimal 32 that's encoded how we've chosen to encode it, which is with the binary form.
So just for a little bit of context on that, when the spec was originally being designed, they designed the type much like the binary floating point in that it was using a binary-based significand, which is efficient for software to implement because computers are largely power of two based. However, at the insistence of IBM for PowerPC, which actually has hardware support and has had it since 2005, and I believe Intel as well. The push was for there to be an alternative encoding for hardware because hardware is able to specially accelerate these types with a different encoding that is not as applicable as the binary-based format if you're doing software-based. And so the solution was they provide both of them. Which is used is technically implementation defined. It's just consistently 32 bits under the covers. And so since we're implementing this in software initially, we'll end up using the binary-based encoding. If, for example, Mono were to provide specialized hardware support for their PowerPC support via Mono LLVM, then we'd likely end up having a couple of these functions intrinsically handled, and the software fallback wouldn't be used, but rather the hardware would instead. And so in that case, decode binary would not just be return underscore value, it'd be the actual conversion. And instead, decode decimal would basically be the, yeah.
So to say it in a really, really nerdy way, if you're in C and you have a decimal 32 star and you reinterpret it to a uint star, the platform you're on determines what the value of that'll be?
Right. They represent the same logical value,
Okay.
but how it's encoded can differ.
And if, 10 years down the line, Tanner, correct me if I'm wrong, we decided that we want that densely packed decimal was a more efficient implementation to use under the hood, we would basically be able to swap that out with no issues, right?
Is there an ABI specification for what folks are supposed to do at interop boundaries? If we wanted to enlighten library import to just handle decimal 32 implicitly, what would we do?
And a variant of this comes from chat, which is which of these encodings or either is lossless round trippable?
Both of them are lossless round trippable. It's just not necessarily lossless round trippable if you if you had a software representation and you were running on an implementation where the ABI specified the hardware support was decimal based, that there was hardware support and it was decimal based, then you would have to choose the right one. And these APIs, if you have raw bits, you're supposed to use these for the boundaries so that you either get a no-op or the correct conversion. It's kind of like Indianness, where you always want to use read int 32 little Indian if you're reading data that you believe to be little Indian encoded. And on a little Indian platform, it will no-op, and on a big Indian platform, it will do the conversion. And so in the same way, if you have data that you've serialized as binary, you would decode it using decode binary, and it would give you a correct decimal 32 for the underlying platform.
I guess let me try and rephrase my question. If I'm writing a C API to share out, and I want to accept a decimal, what do I have in my signature, and how do I document it?
You use so if you're on GCC and prior to C23, you take their special underscore decimal 32 type, and that does the ABI specified behavior on what the format on what the encoded format is. And so the runtime would understand what the ABI requires and understand what the representation of our own decimal 32 is. That is there hardware acceleration or not? And it would know whether or not it needs to convert at that boundary. For C23, this is officially part of the language spec. Same with C++ 23. And you would use the official type decimal 32 underscore T And likewise, that has specified ABI handling, and the same general thing occurs.
And so do we try and do we try and store the exact same layout for our decimal 32 as what C23 specifies for its decimal 32?
So that's where the language spec makes no definition on the layout. The ABI for the platform does. And so ARM64 versus x64 versus Windows versus Unix versus PowerPC could all differ on whether they choose decimal or binary encoding, much like every one of them may differ on big versus little Indian.
Fascinating.
So it sounds like there would be a little bit of work in that department if we decided to switch to the different encoding down the line, because we would need to communicate that.
You need a custom marshal area.
Yeah.
Right. So I guess that just means this type goes on the list of things that have to be, or this type family goes on the list of things that have to be special dedicated handling every time we walk up to a new platform.
Right, and that's also why these are kind of types which the BCL has to provide, quote unquote. No one else can provide them because they are considered ABI primitives. So that's also why we had to provide int128. No one else can provide it because there is specialized handling required at the hardware level and at the runtime level. Whereas int256, we don't have to provide that. Anyone in the world can go and implement their own int256 because there is no special requirements for it. They define it in managed code and it works 100% of the time.
Those statements are if you want hardware acceleration and if you want to seamlessly interop via interop provided by the runtime.
Yeah, if you want to do any kind of interop or hardware support, then it must be in the runtime because it's an ABI primitive.
But with all the work that's gone into custom marshalers, you could write a marshaler that says I'm on a MIPS 32 system. You
cannot. Because you cannot put this in the right register on a hardware that requires it to be registered in that special register, in the decimal 32 specific registers. It's much like you could go and define your own system.single, but if you backed it by uint, then it would never be loaded into an XMM register on x64, or into the by 87 FPU registers on legacy 32-bit. And so even though you've defined something and it implements it correct, and it implements the implementation is correct, the actual hardware and calling convention support is not there because no one but the runtime can define that calling convention support.
Right, because it's the register mapper and the fact that it's a new register family.
Yeah, and then there's also the aspect of custom padding, where decimal 128 has a 16-byte packing, which is not something that a user can define today. That's similar to int 128, vector 128, and other types as well. They all have above truly primitive packing requirements.
Okay. So I guess my next question is, most of the things that I assume that are being on here are things that would be workable with the generic math and generic interfaces, but I don't see any interface that looks like it's going to map decimal 32 to uint. So how is encoding supposed to work generically, or is it not?
Sorry, could you repeat that?
None of the interfaces here say anything about an interface that is binding decimal 32 to uint, which means that from a generic context, I don't see any way that you can access encode decimal.
Right. It's kind of the same as with the integer types in that or the floating point type in general, where on I floating point IEEE 754, there's a way to extract the significand and the exponent, but there's no way to necessarily create something from raw significand and exponents today. because you can't define a size sensitive operation in terms of a generic operation.
So, are you referring to like the trie-right exponent big endian and trie-right exponent little endian operations as the generic way of grabbing those values?
Right. That's the generic way of extracting them today.
Yeah. So yeah, that's right. So that functionality would exist on these types. So you would end up being able to extract the exponent and the significant as a span of bytes. If we wanted to put in code decimal, it would have to be a span of bytes instead of a uint to ulon, a uint 128, which, yeah.
So should we add to this interface, meaning you do it at some potential point in the future? Encode decimal, which takes a decimal and a span and returns the number of bytes it wrote to the span? Or
I think that's maybe something we can review as part of a later API review. It's a scenario which might be important to some niche domains, but it's not the serializing and deserializing data for like interrupt purposes is not going to be a common scenario for generic math, for particularly for these types.
So if we have no more thoughts on this, I think this is probably a good time to talk about the constructor, because it is or the lack of a constructor currently, because it's related to sort of encoding and whatnot. So yeah, just let me know when we should move on to that.
Okay, I took the note down on encode and friends.
Cool. So let's talk about the constructor, I think, at this point, because it's somewhat related. Technically, encode binary and encode decimal can be thought of as technically decode binary can be thought of as a constructor, and decode decimal, but it's not a very intuitive one. Users would have to build their own encoding of the specific value that they're trying to represent. If a user wants to use a specific value, like this, let's say they want to use 1.23 in a program, there are limited ways to do that because of the nature of conversions from other types. So basically, there's no constructor currently exposed. Users could technically convert from float, from double, from decimal, from half, but all of those are going to have problems because they are different sets of representable values, right? So one thing that might be worth considering is exposing what we often use internally, maybe a constructor that takes in the sign, the exponent, and the significant, because the only real way to be able to like take a literal and convert it to one of these types would be via parsing. Parsing could handle every possible value that can be represented. Conversions cannot, and then there's no language literal support, obviously. Yeah, so that's basically the question is, do we want something like that?
We notably have such constructors internally on the binary types. They're just not publicly exposed. And we've not had a need to expose them publicly since you can just write a literal out.
Right. So if we have API on double that lets you get the parts of the double. Do we have an API that lets you then turn them back into a double? Like, have we already cracked that we have parts shape?
I don't think so. Tanner, do you know the answer to that?
Can you repeat the question?
All right, I'm gonna assert that that double is made up of a mantissa and an exponent, and I'm gonna
And a
ignore
sign.
any other details. If you call get mantissa and get exponent, do we have an API that you can give those two pieces to, and it will give you a double again?
We do internally on double. They're not publicly exposed. We
Okay.
use them extensively internally for certain operations, but we've not had a need to publicly expose those. Generically, we have the ability to extract the exponent into significand into a span of bytes or an array of bytes.
Right, but so we
Yeah.
haven't already cracked and decided that we want to do it as like a static from parts or something like that, because most of our number types, ignoring big integer, don't really have public constructors. I don't think.
Right.
But
I think
the,
if we
the
had
majority
it,
of them also. I'm sorry. Go ahead, Tanner.
I was just going to say, I would think if we did have it, we wouldn't want it a constructor, but rather a static create from parts.
I also think it's worth noting, Tanner, correct me if I'm wrong, the ability to extract those parts is implemented explicitly via the generic math interfaces. I don't think you can extract those parts on the type themselves for float and double.
Right. We just have the internal properties. They're not publicly accessible today.
And that would be the same for this type as well. So I think that was a point we talked about a little bit earlier when talking about quantum. You do not currently have the ability to extract those pieces on the type themselves.
I'm not sure if this was said, if I missed it, but also when talking about constructors and creating these things, one thing to keep in mind is most of the existing types have a literal format that allows you to specify the full value just sort of naturally in source, and that doesn't exist here.
Yeah, it looks like so. Int 128. It does look like we gave its parts as a public constructor instead of a static method.
Yeah. And the other one to consider would be half. Half we did not give it a constructor because you can represent every half value as a floating point value. So you can downcast from float to half any value that you're trying to represent as a half. So those are the two examples to look at and how we've handled it in the past.
Right. So again, going back to, we did a whole bunch of work for generic math. If there's going to be on these decimal types, get the 2 tuple or 3 tuple or 7 tuple or whatever it is that actually defines these logically. It seems like a static create from parts would be more generally applicable, unless all their parts are going to have different data types.
The issue with a create from parts is you would end up having to take a generic parameter, which is itself constrained to be number, which causes the concern of the generic code explosion. So today we have the create checked, create truncating, and create saturating, which allow you to convert between two number types. That's effectively how the casting is supported. I think for create from raw, sign, exponent, and significand, it's possible, but I think it would also, because of the generic code explosion cost, would warrant an explicit need from the community on it for the generic context.
Right. So you're saying that I guess it makes sense. We can't just make an assertion that any of the pieces would always fit in a U-long or whatever. So.
Right.
Yeah. Does anybody remember why we decided a constructor instead of a static method for int 128?
I think it was just convenience, and because it's a case where there's never going to be another constructor that might end up being ambiguous as to what it means. U-long a constructor that takes two U-longs is clearly constructing the two parts. You couldn't interpret that as like any other way.
It can multiply them.
That would be weird.
Indeed. But similarly, it seems like here, if we had a, whether we do a named create from parts, just so we're not mixing the decodes being a static factory and then having a constructor, like the three parts as a constructor or as the create method, they don't seem like they're ambiguous. I can't think of another like threeple that you would take that would be ambiguous.
Yeah, I would probably agree. It's going to be a bool sign, a t exponent, and a t significand, where the two t's are uint for decimal 32, ulong for decimal 128 or 64, and then uint 128 for decimal 128.
So the other thing to think about here is that technically there are a couple different ways we could specify each of those parts. We could do integral significant times 10 to the exponent, or we could do like scientific notation, 9.999 times 10 to the different exponent. Essentially, the exponent value is different, is discussed in two different ways in the IEEE spec, depending on like what, with what context they're talking about it. But I think that like the clearest way, actually saying all of that out loud, I think the clearest way to implement this constructor would be the former, where you have an integral significant times 10 to the exponent. We would have to specify to users like what specific exponent we're referring to.
Right. So the way the half constructors work is it's the bool sign, which is just is signed or is not signed, and then we have the exponent, which is effectively the biased exponent. So it needs to have already been normalized for the underlying storage format, and then the significant, which is the just the raw 2's complement representation of the significant. That way, it is a trivial series of bit shifts to construct the value, and therefore it is constant foldable, and can be optimized by the runtime, the JIT, etc.
That's right. I actually had things mixed up in my head. That's the real argument here, is whether or not we want to pass in the biased exponent or the actual exponent. This private half constructor passes in the biased exponent, which would require the user to take the exponent they're actually trying to represent and add the bias to it to make it unsigned. Right now, internally, while working on the implementation, I have a slightly different constructor that takes in an unbiased exponent, and I think it's a little bit more intuitive, but that's up for debate.
Yeah.
Okay,
Notably with...
Go ahead, Tanner.
I was going to say, notably with half, you also have the consideration of things like trailing significant versus actual significant. So it is fine, I think, in general, for binary to be a little bit different. And if the unbiased exponent is clearer and it allows the user to type, for example, new decimal 32 is negative true, and then the exponent of like 10, so 10 to the power of 10. You wouldn't actually do 10 to the power of 10. You'd say 10 because the underlying radix is 10, and then the significant of the value. Then you basically have something that is trivially understandable as, I have 1,000, and I want my decimal point to exist here in that value.
So not
So
that I know the
threefold.
difference between a biased and an unbiased exponent, but if there would be confusion as to which one's required, that does sound like maybe we want from like create from unbiased parts and create from biased parts.
Yeah, potentially.
So
Potentially,
so we would name it
the
because the threeple is different as to what you would give them, but they're the same types, I assume.
I think we've this has come up in the generic math API proposals because the right exponent little endian API, it's either the biased exponent or it's the unbiased exponent, and I can't remember which it is. And I think that speaks to I think that sort of speaks to how unintuitive the biased exponent aspect is, and like I think I would prefer to hide that as an implementation detail and just have users be able to construct things with the exponent they actually have in mind. But
Right. What we expose to the user via the generic math is the unbiased exponent.
Yep.
That is the value that they would understand from a mathematical perspective, and that is not specific to the underlying encoding of the value they're trying to represent. The biased exponent for reference is a unsigned number, so it's basically taking the signed exponent and then converting it to an unsigned number within the bit count that is allowed for the representation. So it's not intuitive to users necessarily.
Right. Because I feel like if I wanted to create the number negative 1,000, that I would say whatever Boolean means negative, and then any combination of, 1 E3 or 10 E2 or whatever to represent the precision that I'm trying to get indicated in the number.
Exactly. Yeah.
And that, so yes, basically doing the scientific notation where you're not allowed to write a period.
Yeah, exactly. So if you wanted to have all of those digits be significant, you would do decimal 32 false 0 1000. If you just wanted the first digit to be significant, you would do decimal 32 false 3 1. And then
wow, you do that order? That'd be weird.
Well, okay, yeah, so maybe it would be the other order.
I mean, like, because again, maybe I'm wrong here, but I feel like the way that you would write that using bowdlerized scientific notation is you saying this is 1000 E0. I am very precisely the number 1000. And so then I would expect the order to be the sign, which was the leftmost part of my number, and then the value, or the absolute value, and then the exponent. So that's the order I would expect the constructor.
I think that seems more intuitive. The reason I have it the way it is because that's the order it's encoded, which is not relevant for the users. So
I posted what I think it could be. We can make it a tuple instead of a thruple, and we can basically have both inputs be signed. So you'd take it for decimal 32, you would take 2 ints. The first one represents the significand, it's signed or unsigned, and then the second one represents the power of 10 exponent. So if you wanted 1000 e negative 3, you would literally write plus 1000 comma negative 3 or minus 1000 negative 3, which is ultimately plus or minus 1, but with 3 trailing zeros.
Right.
And so then it's very intuitive to read, and you can even make the second parameter explicit as comma exponent colon minus 3.
And would this always be all decimal 32s would work with an int, or do we need to go one size bigger for boundary reasons?
We've got 30. You ultimately have 32 bits that are using the underlying format, and so you have no more than 32 bits of significand. You actually have like 21 or something like that, and you've got no more than 32 bits of exponent. You ultimately have like 8 of them. So while you couldn't represent any potential value, using these two. You can represent any representable value using these two parts. You might just have to explicitly truncate off the bits that are unrepresentable, which makes it more easy to see what bits won't actually be preserved.
Except for plus and minus infinity, which I think would come from one of the interfaces already.
Yeah, you would just use dot positive infinity and dot negative infinity on the type.
Yeah, technically this constructor also wouldn't allow us to encode a NAN with a payload, but I don't think that's something that we need to expose to users.
Payloads.
Yeah.
Most hardware disables it.
And then because these are primitive E types, if you specified int.max value with some precision, it's just going to drop the bits it can't represent, or is it going to tell you you've given me an unrepresentable value?
Right, it has to saturate according to the IEEE rules, so it will take the exact inputs as given, compute an infinitely precise result, and then round to the nearest representable. So if you did int max value, you would get out decimal 32 dot positive infinity.
Do the specs specify a constructor that or a function that maps to what we're exposing here?
No, it does not.
So technically we could have that behave how we wanted it to, right? But if we want to be consistent with...
Well, the general rule for computation in general exists, which is infinitely precise and then round. So even if it's not specified, the correct behavior with regards to handling decimal 32 is.
Right. But
yeah.
So int.max value e0.toString would then come back with a bunch of zeros that you didn't expect.
No, that one would represent. That one would come back as well. It depending on if it was considered overflow to infinity or not, it would.
Okay, int.max value minus whatever it needs to be the max value that doesn't coerce to infinity. So
right, then it would end up showing up as whatever the nearest representable decimal was.
Right, which would mean that you're going to end with like 6 zeros. Because all your data is up in the high decimal aspect, I assume.
Right. It's going to take the value you gave, which would be 2.14 E0, and it would convert that to the nearest representable decimal 32, which would either be that exact value or a near value with a couple digits truncated off the end, or infinity, depending on which was considered closest.
Mm-hmm.
I don't want to do the math in my head right now for 2 billion E0.
Exactly. Does that make sense to you, Steve?
I think so.
So, yep. Then the constructor is pseudo-scientific notation, since scientific notation always requires the decimal after the first digit, but so pseudo-scientific notation with the E is the comma.
Yeah.
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 I think that makes sense and people could reason about it, but, looking at seeing who I can bounce off of someone else, I noticed that we have significantly lost quorum. So I'm still fine for discussing generally things, but at this point you can't get an approval. So
do we have a specific name in mind for this constructor? Do we want it to be an actual constructor like with 128?
Given that we've already done a numeric type with a constructor, it's probably okay. Are you guys hoping that we'll get language support for these?
Language support could come eventually, but it's much like with the int 128 type and the half type, where Roslyn has basically said if enough ask for it happens, then language support will be added. It's also possible that longer term they decide to do something like we did with checked operators, where they could provide a general language feature for supporting user-defined constants and user-defined literals. But it's ultimately up to the language team on if that happens and when it happens. And C# and F# have made different decisions on some of the types in the past.
I guess this actually goes back to the ABI question of how are const decimal 32s encoded? I guess they're encoded to whatever the type the system that you would be writing it on would be, but
right.
we're an
It's
abstracted
kind of
type, so we'd have to pick one.
Yeah, it's basically the same as big Indian versus little Indian, and the whole thing with the RVA statics for like uint, where if you return a read-only, if you have a read-only span property that returns a new uint array that only contains constants, that goes through a runtime helper that will decode or encode it to the right thing. And so functionally, if the language got constant support for this, it would likely encode them as some well-defined format, binary most likely, and then it would just call decode binary to construct the decimal from it.
Fair enough.
Or alternatively, it could work like system.decimal does and have a magic attribute called system runtime compiler services decimal constant, because that's how decimal actually works. And it takes the constructor parameters literally, since those are representable by integrals and therefore encodable in attribute metadata. And then the compiler inserts the actual constructor call via lowering.
Okay, so just looking at other shapes of things we have stuff from an interface,
or stuff that was exposed on half. That's not part of an interface, but yeah. The conversions I can speak on, everything follows like a basic formula for convert to decimal 32. If the conversion is lossy, it's explicit. If the conversion is not lossy, then it's implicit. And same vice versa.
Which ones are non-lossy? I don't see those listed.
It must be the bigger types. Cause
it's if you scroll down, the implicit ones are right below this. Yeah. So, yeah, these are the ones that decimal 32 can handle in a non-lossy way. Decimal 64 adds int and uint, I believe. Decimal 128 adds ulon, lon, nuint, nint, and also system.decimal, notably.
Did I lose the battle previously and we said we were going to accept char as a number?
Yes, because the language supports char as a number.
Stupid language.
In general, the list of implicit conversions is basically the same as what the correspondingly sized type for binary floating point would accept. The notable difference is that float accepts int and uint as an implicit conversion, even though those are lossy. And that doubles accepts long and ulong as an implicit conversion, even though those are lossy, and so it likely shouldn't have.
So, I don't remember how we addressed this when we did half and int 128, and I haven't scrolled to see if you're doing partial on the existing numeric types, but here we're having the new decimal types can be created from all the numeric types that pre-exist it, except for big integer, because big integer is always special. And then, so where does the decimal 32 going to a int 128 go? Have we decided on the pattern for that?
Right now it's right here. I guess you're asking, should it be here?
Well, when we did int 128, did we say that converting like the checked cast to an int 64 should live on int 128, or did we edit int 64 and put the checked
we
cast
did not
there?
edit any primitive types to expose, because you don't want to expose new operators on primitive types. So all the operators were on int 128.
Okay.
Likewise for this one. So for this one, we could expose operators on decimal, or we could expose them on int 128, but not the primitive types. But I don't believe we want to. So in particular, these types we're considering put it in system numerics. That way it doesn't confuse people with the existing system decimal. It also avoids the issue of should this live in corelib or not. These types, while people have been asking for the functionality around them for a while, they are not necessarily they're not necessarily types that you're going to want in corelib every time. They're more kind of domain oriented. They're not integral primitives to the runtime, even though that's a confusing term to use. So
essential.
Yes, they're not essential to most code bases, like for example int 64 might be. So putting them in system numerics for the namespace, and likewise having the conversion operators here rather than split between the types where they could be split, means that this type does not have to live in corelib. It can live in system numerics alongside complex and big integer, for the numerics types that people want but may not want as frequently. So it allows it avoids the corelib in the main scenario kind of bloat.
Yeah. Do we care about conversions between the IEEE decimal types? Do we care about where specifically those live? For example, 64 to 128 and vice versa.
Those ones can really be split however we feel is best between the two of them.
Right.
As
do we
long
need to
as
decide
we
that
don't
today,
duplicate.
I guess is what I mean.
I don't know if API review even cares, as long as they're not conflicting with each other.
Yeah, my question's more of, did we have a pattern and we're following it?
There is a pattern for that we've kind of followed with int 128 and in float, half, big integer, and complex, in that conversions from go on one type, conversions to go on the other type. And we did that for because that was the way that the generic math functionality worked best for the whole create from and convert to pattern, because you want to split them between those two as well without having overlapping overload resolution concerns effectively. I don't remember which one is which, but we do have an effective pattern that we're doing there already.
And just to clarify, in this case, we wouldn't be able to put any of these on any of the system.runtime types because the system.runtime doesn't consume.
Right, but it would be the ones you're adding in the same wave would go. Everybody only defines an I can receive my peer type, but when
so the decimal 32 to decimal 64 conversion and vice versa.
But then
right.
all of the I can be converted to a type that pre-exists, or that preceded me in the timeline, is why the uint 128 decimal 32 to uint 128 lives on decimal 32, because uint 128 already existed, and we just say all the semi-primitive numbers, or treat them like the way we would treat all the really primitive numbers, and say that their conversion operators are immutable, put them on the newer type.
It looks like we did conversions 2 are on the type. So decimal 32 would define conversions 2, 64, and 128, whereas conversions from are defined in the other. So decimal 64 would define from decimal 32. Or
Wouldn't that mean that we have two definitions of the same
yeah,
conversion?
no, yeah, sorry, it's conversions 2, so decimal 32 would define 2, 64, and 128, and then 64 would define 2, 32, and 2, 128.
Yeah.
Just
so,
looking at how we did it on int 128,
right.
or
So,
uint 128.
so int 128 has the operator to go to a uint 128, and uint
Yes.
128 has the operator to go to an int 128.
Yes.
Okay.
But
So,
there's
so
four.
things added in the same wave.
Oh no, yeah, that's right.
So you always define going out, and then you define a coming in for anything that preceded you.
Yes.
Okay. That's a pattern.
Yes.
All right. So yes, really, it was. Are we doing the same thing here that we've done elsewhere? So these are all of these from decimal 32s are because the type that it's coming from already exists.
Yeah.
And then so here you've defined the 2s to its new peers, assuming they all get added in the same wave.
Those are the froms actually, but
those are the
we
froms.
We could switch that.
Well, no, that's from decimal 32 to decimal 64,
Oh
so that's
yeah,
still
it is.
consistent.
Yeah.
The names definitely aren't confusing.
Yeah. Okay.
Yeah.
Right.
But it's not even necessarily in same wave. It's at the same layer in the library layering, dependency layering.
All right. And so this is that I exponential is on the IEEE interface and
Yep.
not the
That's
just
right.
floating point.
So a
Yeah,
note
and there's
on
the functions for getting the exponent significant into a byte array.
Yeah, and we're gonna expose we're gonna expose all of the things before inheriting from floating point IEEE 754. We're still gonna expose all of the functionality that is both easy and required and useful, I guess. So which is basically everything but atan2 and atan2 pi.
Right. But if positive infinity and negative infinity are on the interface level that you're not implementing yet, that means that they're currently difficult to use in generic math, right? I guess you would just take doubled up positive infinity and then convert it to the decimal 32 type.
Yeah.
Like you grab any positive infinity and say, please go be this new type now. And that'd be what you have to do until it implements the interface.
Yeah, I think that would work.
But everything that's not marked platinum, you would be expecting to go in wave 1. You just, because you're missing two things, you can't conform to the interface.
Yep, exactly. And because we're missing the 6 or so things that floating point inherits from, which are actually the real problem. When you inherit from floating point IEEE 754, you also inherit from the sign stuff, the logarithmic stuff, the exponential stuff. So
there's like floating point, and then we had like trig, and then the 754 says it's both, presumably.
Yeah.
Okay.
Exactly.
I don't know what compound is, but it says. I assume this is saying compound is something on this interface or this interface's hierarchy, but the interface doesn't have it yet.
We improved it as an extension. It's basically computing compound interest.
So is there anything else on this type that's new?
Not new. I think that there's a couple things in iNumber base that I think might be worth discussing. The ones that I have a note next to. These are implemented explicitly on, that's the current pattern that we're following. These are technically required by the IEEE spec, so I thought it was worth discussing whether or not we want to do those implicitly. That could also just be a separate proposal, though, because we would want to do the same for float, double, etc. Does that make sense?
So radix here would be 10?
Yeah.
Yep, constant 10, and then constant 2 for float, binary, and half. And when I proposed it being a public member, I think there was some pushback on because you have a well-known type, it's effectively a well-known constant, and so there wasn't enough need for it outside of the generic context to justify exposing it as a member. And I wasn't willing to push back at the time.
I still think explicit is a reasonable choice here, but what exactly does quote quote required mean by the specification?
That's a good question. To be conforming to the IEEE spec, we have to expose it in some way. 2 notes: we don't conform completely already because we don't have floating point exceptions and we don't have rounding modes. And the second note is that their definition of what it means to conform, you don't necessarily have to expose the exact functionality. So for example, I think an argument in the past we've had is it is required that you expose functionality that tells you, is this conforming to the 2019 spec or the 2008 spec? And we haven't approved that in API review, but you can make the argument that we are sort of implicitly exposing that, not implicitly in the technical sense. We are implicitly exposing that functionality by using, like, I think Tanner, your argument was like using these types in .NET, and we are advertising 2019 compliance. That is exposing that Boolean.
Right. So in particular, the spec says that the functionality of determining the radix of a floating point type must be possible. It does not necessarily specify how that functionality must be possible. And so by virtue of exposing this member and then saying you have to do something like public void get radix of t, where t is I floating point of t, and then do return t.radix, we have still fulfilled the spec requirement of providing the functionality.
Right. And you could also say
as would by the very nature of this type representing this one and only thing, it would also seem to meet the spirit of it to say, like, if you wanted, you know, if type of whatever equals type of decimal 32, return 10. Like that would also logically meet the spirit.
Because we're a strongly typed system, you can say that use of this type means your radix is 10.
Right.
Correct.
Sorry, go ahead, Tanner.
I was just going to say the main argument for providing it outside of the generic context is things like source generators, making it more trivial for devs to generate source without having to special case things. But I don't know of any cases where users are using these types in source generators, and we do have the fallback of you can use generic math. So it's something that I still think would be nice. It fits in with the other kind of constants we've exposed on these primitive types, but it's not something that I was willing or am willing to fight API review on.
We also have the fallback of we can always expose it public in the future.
Yeah.
Yeah, I'd be inclined to, if we think there's something that a developer using the type just isn't going to use directly. I mean, that you use it in a generic context when you don't know what the thing is. But if you're using decimal 32, are you really going to access .radix? I'd be inclined for anything where we say probably not, to start with it not exposed, and then we have the choice later if we want to.
I agree.
I'm also following suit with what we following suit with what we've done with other types here in the past.
I think is canonical and is 0 might have a little bit more justification to be exposed. I need to double check if decimal 64 equal 0 will just work, because we could argue that that's how we're exposing is 0.
Yeah, that's how that's why we don't expose the is 0 method for float and double, because comparison against 0 does the right thing.
Does it do the right thing with the context of the cohorts, where 0 can be represented in multiple ways, but I believe it's arithmetically.
For binary, there is no cohort, so
That's what I'm
doesn't
saying.
matter.
So in this case,
yeah, I believe, if I remember the decimal spec correctly, the decimal spec requires equality operation between 1 and 1.0 to return true, and so therefore it would work correctly with respect to cohorts.
Yeah, that sounds right to me, from what I remember. So yeah, in that case, we don't need a 0. Is canonical.
Given the fact that they're encoding significance, does that even have meaning here? I mean, I guess you can be the canonical nan, but anything other than nan seems like it only has that every value actually means something different.
So the canonical, so for the reason this is explicit for binary floating point types is because there's not really a concept of canonical representation.
Yeah.
For decimal types, the canonical representation is effectively the scientific representation with no zeros, with no trailing zeros. So 1 would be the canonical representation. 1.0 would not be. And so for decimal, because of the cohorts and because you can have multiple representations of the same number, there is in fact a canonical representation. And knowing that may or may not be important to some users.
Okay, so that's not you're the canonical representation of this value, but you're the canonical representation of, let's call it the integral representation of this value?
Well, it also applies to like 1.2 is canonical, but 1.20 is not.
Yeah,
that's
why
actually
I've
know
kind of
if that's
hand waved
true.
over integral.
It's the spec exact wording is that that canonical numbers use the preferred exponent for the value, and I believe the preferred exponent is always the capital Q, which should be the one which is effectively a specific number of trailing zeros, which I believe is none.
Well, but the notation that Drew shared is Q of x is the same as quantum, which is the precision. So that means 1.0 is canonical for being 1.0.
Yeah, I'm looking at 3.5.1, the section that describes cohorts, and I looked into this a little bit and I couldn't find, and I should have looked a little bit deeper, I think. I couldn't find a mention of a linking of canonical to the cohorts themselves. It does explicitly use the word canonical when referring to both non and infinity. I don't know if there's a preferred encoding returned on an arithmetic operation, but that doesn't necessarily mean that the preferred encoding is canonical, because under your definition, I believe, it might not return the canonical, the one with no trailing zeros. It might return the smallest of the two.
So the canonical encoding is the preferred encoding of a floating point representation. It applies to declets, significance of finite numbers, infinities, and nans, especially in decimal formats. And then there is, in binary interchange formats, all numbers and nan encodings are canonical. And then the exact canonical encoding for a nan means that bits G6 through GW plus 4 are 0.
Mm-hmm.
there are two canonical encodings of infinity due to positive and negative, but they ultimately have G5 through W plus 4 being 0 and T being 0. And a canonical significand only has canonical declets. I believe it's ultimately essentially the trailing zeros, but I might be slightly wrong or misremembering on that.
Yeah, I think I got a different impression, but we can also talk about that.
Yeah, the point
offline.
is that
Yeah.
there's a canonical encoding and non-canonical encoding for different numbers or decimal, whereas that's not the case for binary floating point.
I thought there was I'm the canonical Nan.
For the purposes of is canonical for binary, all nans are considered canonical.
The literal only thing I could ever think of that function would do, it doesn't do.
Yes, I know.
Yeah, on that one, I'd say whether or not it's useful to somebody, the fact that nobody knows what it means let's just not make it public
Yeah,
until
that's
someone
fair.
asks.
Um,
It answers a question. What question does it answer?
Actually, I
you
think,
need a PhD to understand.
yeah. Yeah, I think that argument is reasonable. If it's needed down the line, we can expose it. Yeah.
And it being through generic math means that it is in fact exposed for users.
Yeah, that's true. Yeah, because they can cast to iNumber base if they really need to. Cool. Yeah, so we're gonna leave all of those as explicit. I think that might be it. If you keep scrolling.
Sorry, what's the definition? There was a method is odd integer. Just curious, what's the definition? And is even integer?
Yeah.
Is that basically? Is it an integer? Like it? There's nothing. Anything after the decimal point is all zeros.
Correct.
Okay, and then is that first part odd or even?
Correct. So 1.2 would return false from both because it is because when you have fractional data, it is not considered an integral anymore.
And then is finite? What's an example of a decimal that is finite would be false?
Infinity.
Oh,
and
I see.
Nan.
Okay. Okay.
I knew the answer to one of these.
And we need both is finite and is infinity because there's three things. It's finite, infinite, and Nan.
Right. And there's also the performance aspect. Checking for just is infinity is cheaper than checking is not finite and is not Nan, for example.
And checking is finite is something that people will frequently do?
Yes, that's the typical check at the beginning of most math functions to determine do I need to do special handling or do I need to do regular handling.
I see.
Typically you'll do if is not finite and then within that you'll have the check for if is Nan. Then do the Nan specific thing, otherwise do the infinity specific thing.
Okay.
Oh, actually, I also want to clarify that is odd integer is not from the spec.
Right.
That's an iNumber base.
Trusting in your nomenclature here, it's all of these functions are defined because of iNumber base, and this is
exactly.
what's being redundantly public and what's not. And
yeah,
as long as you're not actually defining anything new here, then it seems reasonable.
Yeah, exactly. Yeah, this is mirroring exactly what the existing types already do.
Yeah. Is even integer and is odd integer were notably ones that we approved and implemented in .NET 7 late stage because There are APIs that people have been frequently asking for a while. It's kind of the same as the is-odd package for npm, where it's technically trivial from one aspect, but then there's performance and other number types where it starts getting more complicated. And so people want to know, am I dealing with something that is an odd or even integer, and do that check efficiently for me, particularly when considering negative numbers and floating point numbers and every other thing.
Yeah. Yeah, and I think that's it.
Okay, so yeah, so the things that are not just from the interface sys are the encode routines and the constructor, right?
And conversions.
Conversions, quantum, quantize. It's
Fair
from an
enough.
interface, but it's from a new one. And there's some parsing and formatting stuff that is not from an interface, but is mirroring what half and float do.
And decimal.
Yeah, and it's
believe
put
so.
all the primitive types exposed. So it's like the convenience method of toString that only takes a format provider and does not also take the string format, which we've exposed on every primitive type so far.
On that note, are there any format strings that we need to be thinking about specifically for decimal 32, or is it just work with the numeric ones and there's nothing else that's necessary?
It's the same formats as float and double.
Okay.
So you basically still have the same consideration of you've got an infinitely precise finite number that you're parsing and then converting, and then nan and infinity.
Okay.
Because the toString, presumably the general toString you would want on it would do 1.0 and 1.00 differently depending on the quantum value.
Right.
But is there... So would we need a format string which is print it using its significance if it's lower than the number I give you, otherwise cap it at the significance? Or is that just something somebody's going to have to write themselves?
So
I wanted it of up to 3 decimal places, but if it's encoded with sigfig to say it only has 1 decimal place, don't write 2 extra zeros.
Right, so it would work like decimal does with regard to trailing zeros, and so toString by default would round trip all represented data. So if you had 1.00 represented, it would print 1.00. If you wanted more or less digits, you would then have to use the toString that takes a format specifier, and you would have to say, for example, E2 if you only wanted the exponential format with 2 significant digits, or N1 or G3. All the standard numeric format specifiers and what they mean would be.
But E2 will add zeros that weren't actually there, right?
Right.
Yeah,
you can add or remove zeros that were or were not that were there or were not present. So you'd have to with some of them.
So if you wanted to do, again, this is made up. It's just the most likely thing that I could come up with that was made up of. So if you wanted to do the don't write zeros that aren't real, you need to understand the quantum yourself. If you also want to cap it.
Right.
Yeah, so if I have...
You could also use a custom format string, which will do the right thing as well. You can say, with a custom format string, you can say print me all integral digits, and then you can say print me digits if they exist but not if they're 0 for the decimal point with a custom format string.
Right, but that's whether or not they're 0, not whether or not they were significant.
Right. Well, it's saying that if there is trailing 0 data there, print it. Otherwise, don't. So you can basically say don't print any non-significant not you can say print me all the significant digits and not any non-significant digit represented using a custom format string.
Fair enough. And given that we have our weird quanta here, which I don't think our existing decimal has for integral values, if I have 1E3, so there's only one digit of precision in it, is the toString on that going to write 1E3 or is it going to write 1,000?
It depends on if you're so the toString takes into account the exact value being 1,000, and it will then print it. So G prints to using either general format or scientific format, depending on which is considered quote unquote shorter. So I think the actual cutoff is like 5 digits, and so if the literal is more than 5, if the exact number is more than 5 digits, it will switch to exponential format, and if it's less, it will print it as an exact number. So 1E3 should print as 1,000, whereas
really.
1E6 would print as 1E6.
Notably, if we want to conform, we're going to have to be able to round trip to the right cohort member. So that I don't think that necessarily has to be the default behavior of toString.
Well, that'd be the default. Is it would ensure a round trip.
Well, that's what my if I called the constructor with 1E3, then that's writing the decimal 1,000. You've added digits of precision that I didn't give you.
And when that gets parsed back, it'll get stored as 1,000 E0, which is not considered to be like a correct round trip.
Yeah, so we'd have to ensure that the relevant data is preserved, just like with decimal.
So I guess, well, because decimal has double has R, but I think you hate that type or that specifier.
We fixed R to be the same as toString.
Because it seems like the R format on the decimal types would end up doing you called the constructor with 1.3. I'm going to print 1E3 because that's all the data I have. So you need to load back as 1E3 and not the number 1000 E0.
Okay, yeah. So the general point is that toString by itself is meant to be the round trippable. That way people can do toString and then parse the result back and get an identical bitwise value as to what they originally had. And then if they want a different behavior, then use a standard or custom numeric format specifier. So if we need to preserve information with regards to parsing, we would do that with toString and R.
Okay. Which will be interesting and weird that R on this type means you might start seeing scientific notation for integers. Of just like, yes. I need to tell you there aren't real zeros here. So.
Yeah. Which is a real use case, I feel like.
Yeah.
But
well, there's also the case where you already end up in kind of that weird scenario with half, where half dot max value is technically 65504, but it prints as 6.55 E3, E4, whichever one is right, because there's only three significant digits needed for rounding to the nearest representable result.
Fair enough. But okay, so I am gonna have, because we don't have quorum, I'm gonna call this needs work, but I think when it comes back up, well, because I have to mark it as something or it won't show up in the email. And then I'll send the email and I'll mark it back as ready for review.
Okay.
But so on review, it would just be the constructor, because we discussed that after we lost quorum, and then making sure that we all agree on the plan for which way the conversions go, and then we call that the pattern and don't have to talk about it anymore.
Yeah, because I think everything else was discussed while we had quorum.
Did I anticipate your question, Steve?
Yep. Thank you.
Yeah, so it's basically
to make sure we didn't have another 2-hour meeting on it.
Yeah. So it's just
It should be a
like
5-minute.
the shape of
convention.
everything else is the interface says to do this, plus the 1 2 string overload, and then, but the constructing from parts, so that it would be a constructor and that we're going to use the pseudoscientific notation.
Yeah.
And then for next time, you guys need to come up with what those 2 parameters are called.
Do you
I
think
assume one
that
of them's
those,
exponent, but
Do you think that those 2 points, considering they're so small, is something that we could just send to API review email?
I mean, you've seen the response rate to the DL.
Right. People say, "Here's my idea." If no one says no within the next 24 hours, I'm doing it.
I think I'd like the constructor versus a static factory to make sure we actually have people look at it. So I don't anticipate a long time on things, and I think that's going to be the only possible point of contention.
Are we expecting Tuesday, or is it going to put this at the back of the queue?
So Emo
Because it's
sets
up
the
to Emo,
agendas, not
yeah.
me, but
Yeah, fair enough.
I would expect that this gets to come up as we just need 1 point of overflow to sign off on it. So I would put it at the front on Tuesday, but he may have,
Cool.
if he promised like win forms that they get the first slot, you may be second.
Fair enough, yeah.
Okay. So yeah, we had some chat, but none really after we lost quorum, and I will.
It sounded like there was a conversation about iConvertible in the chat. Was that resolved, Tanner?
Mostly it was just Levi commenting about iConvertible and me saying iConvertible is a legacy interface that we can't really version and we don't want to version, and that the support that he's looking for is something that we're trying to look at from the kind of like bridging generic constraints perspective, which is the general of I have something like an object which is under constrained or has no constraints, and I want to call something like iNumber t.create checked, which has a constraint. It's a general issue with generics, and generic math kind of hurts because of it in these cases where it does come up.
Got it. Yeah. Okay, cool. That's it then.
Okay. So there's those notes, which includes just the future consideration of how encode and decode could work generically, but that's just of consider. And yeah, so your real homework is come up with the names of these 2 parameters.
Yeah. Should I put that on the original post? Like edited it in?
Yes,
Edit
please.
it in. Okay. Perfect.
We're only good at looking at the top item.
Yeah.
I'm just
good.
curious, this doesn't have any bearing on the discussion, but Drew, you've been looking at this a lot. Have you been prototyping? I'm just curious how far along with the actual implementation we are, or if now like we start from scratch and get going.
Yeah, no, I've been prototyping. Right now I'm working on decimal 64. I think it's hard to say exactly how long it will take, but like I'm hoping to get that done by preview 3, I guess.
Mhm.
Yeah, and then move on to the other ones. But yeah, implementation progress is going well. We have an open source Intel library that we can borrow a lot of stuff from. It's a C library, but I've been doing some porting from that. Yeah, I think ignoring the platinum stuff, I think getting like one of these types ramped up is not like it's a lot of work, but it's not insurmountable.
Got it. Thanks.
Mhm.
I guess one last question.
Yeah.
So, how does someone decide which of these? Let's assume that all 3 of these types are, for all intents and purposes, better than system.decimal.
Yep.
out of the three, which do they use? Is it based purely on the precision that they, and kind of the range that they care about? Is there a performance factor to it? Is like what's the matrix of decision look like?
I would say that the decision matrix is going to look similar to how users evaluate the different integral types. So depending on those exact two factors, the range of representable values as well as the number of digits of precision that they need, they're going to want to go for the smallest type that can fit everything they want to fit.
Do we, on the extension types that we've added, like int 128, etc., do we tell people if they're hardware accelerated?
We do for the vector types. We've not done that on any of the types like int 128 or half yet. We generally just expect that we're providing decent performance for them. If there was hardware support and it was worthwhile for users to know, we could expose. We have a well-known static property is hardware accelerated. We've exposed for vector types, so we could.
Right, because I could imagine that decimal 32 and 64 might be hardware accelerated on a platform that 128's not, and then now you get the well, am I getting this in one instruction or a lot, and do I need the extra precision that much?
The spec requires 64 and 128 for all systems that implement the spec, but that is not necessarily always followed exactly. But that might be what we would expect, is that those two would be on most systems, and then decimal 32 would be sort of the add-on.
Notably, decimal 128 provides a little bit more precision and range in the same amount of space as system.decimal. But that's also, most people aren't going to need 34 digits, even if they're doing extreme currency situations. And decimal 64 is kind of like double, where it is a good balance between precision and speed. And notably, there's the well-known post from NASA on how many digits of pi do you actually need. And NASA uses 16 digits of pi, which is exactly how many fit in a decimal 64. So decimal 64 kind of ends up being the right balance. And then you've got decimal 32, which is similar to float in that it is smaller with less precision, but for a lot of more performance-oriented domains, it is the more optimal choice to use for those. And so it's really just going to be, most users will probably want decimal 64. Some perf-oriented users will want decimal 32, and some users that are working with really big numbers will need to switch over to decimal 128. In general, we expect decimal 64 to be kind of good enough. That's why that's the first one we're focusing on adding, and it should provide a significant performance advantage over system.decimal or system numerics decimal 128.
Thanks. So I think the short answer to my question is, like, the too long didn't read is basically start with decimal 64 and then go up or down if reasons.
Yeah.
You mentioned pi. Like, we have some well-known constants on math.pi, math.e, math.tau. Like, do we? Can you just cast those from double, which I think they're defined as, or maybe they're float? I don't remember, to decimal 64, and the full however many digits we expose there will round trip just fine?
We expose them as properties on the type, just like you can do float.pi now.
Got it. Okay.
And I would assume that we don't want to make the conversion operators ask, is this exactly float.pi, and then make it more precise when it's up converting it.
Right, because that would end up leading to bugs in various cases.
Yeah.
Just curious. So decimal 128 has up to 34 digits of precision. Does that mean decimal 128.pi also is 34 digits of precision?
Yeah.
Okay.
Using somebody's well-established 34 digits of pi?
Yeah, well, in the case of decimal, there's not going to be rounding necessarily. There's going to be namely truncation in most cases. So unlike float, where you end up with like 6 accurate digits and then an indeterminate number of inaccurate digits after that, this will be exactly the first 34 digits of pi, with the last one maybe having been rounded up if the last one was a midpoint, if the 35th digit was 5.
But not if the 35th digit was 9.
No, so if the 35th digit was 9, it would also round up.
Oh,
it would
okay.
follow it would follow the normal rounding rules, with midpoint with exactly 5 being round to even.
Got it. Okay. I thought you were special casing 5 and 5 alone. I was very confused.
Yeah, I was trying to say 2 things in my head at once.
We need a new rounding rule on our enum option.
And then again, just for people's decision matrix in the future when this comes up, if the expectation is the processor people only care about 128 and 64 and 32 software, then the perf advantage of it would be that an array of them is more compact, but they may be slower to operate because they may all be using a software fallback.
Yeah.
Right.
That's kind of how we're treating half right now as well.
Yeah.
Okay.
Yeah. You would end up using like half, where you use decimal 32 as a storage mechanism to save space, and then you would use an efficient upcast hardware, even if they only provide support for 32 or for 64 and 128, would likely provide an accelerated conversion from 32 to 64. And so you can use the efficient storage format, operate in the larger type, and then downcast. Which is how people use half and bfloat 16 today.
Yeah.
Fair enough. But, where we have float and double, float was the float until we got better processors, and then we got double, and it's like, well, you can use float. The processor still has those instructions there. They didn't delete them yet, so. But I guess half already has that. So, all right. Well, yeah. In general, this looks reasonable, but as we haven't really built back up to full status on Thursdays, and we lost a bunch of people at 11. That's the only reason I marked it needs work.
Yeah, sounds reasonable.
So
should hopefully be an easy Tuesday review.
Yeah.
With that will not take 2 hours.
Yeah. And then I'll send Emo a note for scheduling for Tuesday to let him know this should be as early as hasn't already been promised, because it's just a group sign off. So. And don't forget your homework. Name the 2 parameter constructor, or the constructor's parameters. So.
Will do.
All right. And with that, I declare it to be lunchtime. So thanks everyone for joining us online, and thanks Drew and Tanner, and thanks Steve for staying with me the whole time.
Thank you all.
Yeah, thanks everyone.